Great. Yeah, okay, good. Can I use the mouse, do you think, maybe, to go? Or I'll lean over, that's fine. Okay. So I just want to do a brief recap on compactness, which we went through quite quickly last week. So I guess the idea is just like, so we were talking about, we say that a locale is compact if whenever you have the product of it with some other locale, the projection onto that other locale is closed. We kind of argued that's the right notion. And so we care about what it means for a map to be closed. So of course it means mapped closed sublocales to closed sublocales. And we notice that this is kind of equivalent to this adjoint satisfying a certain Frobenius reciprocity type condition. And then we kind of spoke about this other notion of compactness. Thank you. So this other notion of compactness, which is more like what you would expect the definition of compactness to be, about having these finite subcovers. And we mentioned that it's equivalent to, rather than saying that every cover has a finite subcover, you can say that every directed cover contains the kind of top element of the frame. And then furthermore, we showed that a space is compact if and only if the right adjoint to this unique frame homomorphism from omega into the frame preserves directed joints. So this ends up being equivalent to this property for all directed covers containing the top element. So this is equivalent to being compact. Okay. I don't know if there are any questions about this or anything, or anyone wants me to go through more about that. Okay. So now it turns out a very useful notion to consider here, I guess, because we know that being closed is important for compactness, and we know that right adjoints preserving directed joins are important. This motivates this definition of a locale map being called proper. So this is if it's closed and its right adjoint preserves directed joins. And this is also related to the notion of a proper morphism of topological spaces. And now we have kind of a kind of equivalence of a number of different concepts, which is very much like the thing we spoke about last week for openness. Except these first two are slightly different. We didn't have something like this in the last case. And that is that this projection being closed for all y is the same as the projection being proper for all y. So this is probably the hardest part of the proof. So we aren't going to talk exactly about why this is the case. Certainly the proper implies closed, that's trivial, but that the closed implies proper is not obvious, and it really uses the fact that this is true for all y. If you just have a single projection being closed, that doesn't mean it's proper. So this is kind of a difficult result. But the other ones are very similar. So once we kind of buy that, the fact that 2 implies 3 is immediate by taking y to be the terminal locale, and then 3 implies 2 is because you can prove that proper maps are fallback stable. And then the equivalent of 3 and 4 is again very similar to like what we saw for openness, where the Frobenius condition ends up holding for free in the case of this terminal locale. So that's, again, it's all very similar to the open case. And then we have results exactly like the open case, completely dual. So rather than saying, before we had an open sublocale of an overt locale as overt, and now we have a closed sublocale of a compact locale as compact. And we have that images of compact sublocales are compact, and we have that binary products of compact locales are compact. And again, this is kind of, it's very easy to kind of think about why this would be true. So for example, for binary products, you can just universally quantify over the first factor and then over the second factor, and that universally quantifies over the pair. So again, it's kind of a lot of intuitive kind of understandings of all of these kind of results. And it's not very difficult to show that a set is going to be compact if and only if it's Kuratowski finite. So I mentioned last week that in some sense, if you start with this definition of compactness in terms of these closed projections, then this kind of gives you the notion of Kuratowski finite for sets. So it tells you that this is like the good notion of finite in the sense of being compact. So that kind of, I guess, motivates this property to some extent. And it turns out I haven't really spoken too much about this before, but we briefly spoke about this idea of what ends up being called Bishop finite, which is with Kuratowski finite, you can list the things, but there may be repeats in the list. So if you require that there aren't repeats in the list, this is the same as saying that you can actually check when two elements of the set are different. So this is saying you have decidable equality. So these ones correspond to compact Hausdorff sets as opposed to just compact sets. So again,
when you have a bijection with the
yeah, exactly. When there's a bijection with this finite, finite, like obvious finite numeral. Yeah, exactly. So kind of compact Hausdorff and the and compact when applied to sets both give us kind of two interesting notions of finite, which are important in constructive mathematics. So again, I guess it's weird to have different notions of finite, but when you think of it from a topological perspective, that some things are compact, some things are compact Hausdorff, maybe that makes more sense. So there's a theorem which I won't prove, but again, you can look at my lecture notes for. I think I do prove this result. Yeah, I think so. So that the kind of closed interval from 0 to 1 is compact. It's a completely constructive. However, it's possible you might have heard some constructivists say things like the closed interval is not compact, or the Cantor space 2 to the n is not compact. But they aren't referring to this locale, they're referring to the topological space of points. And so what this is really saying is that we know that the localic versions always are compact. So if these are not compact, that means that they must fail to be spatial in these cases. So if someone says that this interval is not necessarily compact, or Cantor space is not necessarily compact, they're referring to the topological space of points. But the locales always are compact. This means that they can't be spatial. So this is kind of telling you that this real closed interval might fail to be spatial constructively, but the locale will always be compact. So a kind of important example is the effective topos. So you can think of this as the universe where everything's computable. So in the effective topos, the locale of reals isn't spatial. And so if you take the kind of set of points of the locale of reals and take that topological space, then there's a computable open cover that doesn't have a computable finite subcover. And there's this nice article by Andre Bauer that kind of constructs such a cover using this thing called the Kleene tree, which is an infinite computable tree that doesn't have a computable path. So if you have classically, if you have an infinite tree, there must, and it's a binary tree. So an infinite binary tree, there must be an infinite path. Yeah, but like if you're in like computable universe, you can have a computable tree where there's no computable infinite path. So that is what allows you to build this kind of open cover that doesn't have this finite subcover.
And so it not being a computable path means there's no program that will tell you when to turn left and right so as to be infinite.
Yeah, exactly. There's no program that outputs the sequence of left, right turns. Yeah, that works. Yeah, but it's computable. Yeah, but that doesn't exist. So it's not a complete binary tree. It's not a complete binary tree. So you can't go left. But
Ja? Hè? Alsjeblieft, ja. Met mijn eigen melk. Ach, met de normale melk, alsjeblieft. Nee, jelle melk. Dank je.
Okay, it's fine. Okay, good. So that's what I had to say about compactness. Does anyone else have questions or any comments? Okay. So the next thing I want to talk about is, well, what I say here. So the idea that if we do things in the point-free way, many principles that people say are classical principles that don't hold constructively do actually hold constructively. And I mentioned this, I think, once after one of the lectures. And this is kind of a stupid example, but I still think it's maybe worth mentioning. And that is this idea of excluded middle. So constructively, we don't have excluded middle, right? But what we can do is so it's not true that for a set, like a subset has a complement. But on the other hand, it is true that if you view the set as a locale, every open sublocale, so every subset corresponds to an open sublocale. This always does have a complementary closed sublocale. So it doesn't have a complement as a set, but it does have a complement as a locale. It's not true that every sublocale has a complement, right? Okay, so it's not exactly as good as excluded middle, maybe, but the things that you're talking about, like a particular subset, will have a complement as a sublocale. So this you can sometimes use as some kind of replacement for excluded middle. But maybe a slightly more interesting example is Tikhonov's theorem. So it's famously true that, or a famous result of Tikhonov's theorem is equivalent to the axiom of choice. So this is true for topological spaces. But for locales, it's just always true. Always completely constructively, no choice principles, nothing. That an arbitrary product of compact locales is compact. So yeah, this is just a theorem. So in particular, this tells you that, I guess, tangent space is compact as a locale. It might fail to be spatial. So if you try to kind of recover the classical results where you're using choice is to prove that these products end up being spatial. Okay, but what about the axiom of choice itself? So the axiom of choice, of course, it's a really well-known example of something that's not constructive. But one way to phrase it is saying that the product of non-empty sets is non-empty. So we must replace non-empty with a good notion, right? Something like inhabited. So we can say, is it true that the product of inhabited sets is inhabited? And the answer is no. But it is true that the product of inhabited sets in the category of locales is a non-trivial locale, at least if the set you're taking the product over has decidable equality. So that's a bit of a wrinkle, but classically everything has decidable equality, right? So it's in fact true more generally if you have a collection of overt positive locales. So I don't think I told you what a positive locale was, but I told you what a positive element is. So a locale's element, if its top is positive, if its top element is positive. So that's maybe reasonable. It turns out it's equivalent to the unique map to the terminal object being an epimorphism. Yeah.
So, and why this doesn't give the same result in the spaces is because the products are different.
Yeah. So the products in general of locales and spaces don't agree.
But in the cases where they're the same, this would be true.
Yeah. So what's always true is if you take the products in locales of like spatial locales, and then you take the spatial reflection. Or I guess I'm thinking with frames where it's a reflection. With locales, it's a co-reflection. Then that will give you the usual product. So in this case, you get a non-trivial locale, but maybe it has you can't prove that it has any points. So it might be that its spatial co-reflection ends up having no points whatsoever. But it's still non-trivial as a locale. So the usual axiom of choice is saying that this locale you get actually ends up having points. But in this case, you can't prove that it has points, but you can prove that it's non-trivial as a locale in this good sense. So so it's always true that a product of overt positive locales indexed by a set with decidable equality is both positive and overt.
Is there an analog or like some way to actually get something that looks like the axiom of choice in the setting, like that's equivalent to that?
So I mean, this does look something like the axiom of choice.
No, but in terms of an actual function that's choosing.
Yeah. So I mean, it ends up being the same thing, I think, but you can phrase this in terms of imagining like you have like, yeah, you can I'm sure phrase this result in a way where you have a certain morphism between certain locales that satisfies certain overtness, openness properties, and consider the space of sections of this morphism and show that the space of sections is non-trivial. Yeah.
Okay. And so it may not have a point, so the function might not exist, but somehow the space.
Yeah, exactly. So there may not be a section, but there'll be a space of sections, and that space of sections will be non-trivial. And you can use this result to do many things that you don't, it often ends up being the case that you don't actually need to have an actual point in order to do what you want to do. So you can consider the space of all of these things and then do like a whole lot of results and get kind of prove a result, and you never actually needed to take a particular point. So in this way, you can really use this result instead of the axiom of choice. So yeah, so this is due to Simon-Henry, and it's in this paper, localic metric spaces and localic alpha duality. But do use the version on the archive, the second version, because the original one had a mistake in the proof. Okay, so yeah, so these are some three things: excluded middle, Tikhonov's theorem, axiom of choice, where, okay, the precise statement didn't quite go through, but the kind of localic version, in some sense, does end up being true always. And often, you can just get by using the localic version. You don't need to use the version which isn't true constructively. So I think this ends up being like very useful. If you want to do constructive mathematics and you still want to use things like the axiom of choice, you can often get away with it. And it ends up being completely constructive. So we aren't going through all the details. So you can, again, look at the lecture notes or look at these references and things for the details. But I guess it's just a good thing to know. Okay. Any questions about this? Okay, good. So for the next half of the lecture, I want to talk about an application of all the stuff we've been doing. So we've gone through 4.5 lectures on constructive point-free topology. And maybe you're thinking, I really don't care about constructive point-free topology. Like, I want to do things classically, or I want to work with classical topology, or something like this. And well, hopefully, what I've said at least convinces you somewhat about constructive point-free topology. For example, the previous results, that maybe there are reasons to do things constructively, like, for example, you want to have a computer program or something. And then maybe it's useful to use locales to be able to use these classical results. But we'll now talk about an application which will give you a result in classical topology. So even if you only care about classical topology, we will have something that tells us something useful about something that we care about. So what we're going to do is we're going to prove a constructive version of the extreme value theorem. And so remember that classically what this says, it says you have a compact topological space, and then whenever you have a continuous map from the topological space into the reals, it attains a maximum value. Okay, and yeah, this is based on a proof by Paul Taylor in a slightly different setting, but it can also work with locales. So we're going to prove this constructive result, and then we're going to like interpret it in a certain topos and get a result. Okay, so we want to talk about extreme value theorems. We're talking about maxima, right? So before we talk about maxima of functions, let's talk about maxima of like sets of real numbers, right? So classically, the real numbers, I mean, one of their defining properties actually is that whenever you have a bounded inhabited set, it has a supremum and it has an infimum. And now this very important property of real numbers classically completely fails constructively. So if you have a set like this, so it contains the element 0, and it contains the element 1 to the degree that P holds. And you ask, what's the supremum? Well, suppose this has a supremum as some real number. Well, either this real number will be greater than 1/3, or it will be less than 2/3, right? It's always true that any real number is either greater than 1/3 or less than 2/3. This is actually, it was one of our axioms of Dedekind cuts, was something like this. So we know that must be true. But if it's greater than 1/3, then we know if the supremum is greater than 1/3, we know that it must have been it must have had this 1, right? Because 0 certainly isn't greater than 1/3. So it must have included 1 in the set, which means P must be true. And if it was less than 2/3, then that means 1 must not have been included. So P must be false. So if this has a supremum, then we have either P holds or P doesn't hold, which is excluded middle. P could have been anything. So having that arbitrary sets have a supremum, arbitrary bounded inhabited sets have a supremum, gives you excluded middle. But we still want to talk about suprema. So what we do is we need to kind of change the notion of reals we're talking about. So we might want to complete Q under inhabited suprema. And this will give something different. It won't give us this what we had before. The real numbers we had before are called Dedekind reals. And this gives something different. It gives you a lower real. And what's different between a lower real and the Dedekind reals we were talking about before is before we had a pair of sets. So we had the pair of lower bounds and the pair of upper bounds for the real. But for a lower real, we only have the pair of lower bounds. So these are reals which are only described in terms of what rationals you can like approximate these reals from below by rationals, but not necessarily from above. So that's the concept of a lower real, and the supremum of a bounded inhabited set of reals will always be a lower real. And in fact, you can do the same thing with a set of lower reals. It will still be a lower real, but it won't necessarily be a real. But it makes sense, right? If you're taking the supremum, you're kind of approximating the things from below. So it makes sense that will give a lower real. I guess the unfortunate part is that it doesn't give you a Dedekind real. And we can do the exact same thing on the infima, and we get something called an upper real. So an upper real is a real that you can only approximate from above.
Why does that not run into this issue?
So in order to do this proof, I said that it must either be greater than 1/3 or less than 2/3. But with these things, you can only either compare from the bottom. So you can say for a lower real, you can say when it's greater than 1/3. And for an upper real, you can say when it's less than 2/3. But you can't say both of them in this case. So yeah, so the proof doesn't go through. Okay. So we now might want to talk about a locale of lower reals, right? Or something like that. So we can phrase it as a geometric theory like we did before. So we just now have the lower set. And remember, we had all these axioms of Dedekind cuts involving the lower sets and the upper sets. So we just throw away the ones involving the upper sets. And we just end up with 3 axioms. So it says that if Q is a lower bound for our real, and if P is less than or equal to Q, then P is also a lower bound. If P is a lower bound, then there must be some Q greater than P, which is also a lower bound. So this is this fact that we say that the set of lower bounds is rounded. Essentially, it means they're strict lower bounds, right? It's not like just less than or equal to. And also, there's this inhabited condition that says for every lower real, there is some rational which is smaller than it. So you can't be like at negative infinity or something. And OK, we can phrase it kind of geometrically, and we can arrive at a presentation for a locale. So the first 2 conditions give us this equality, this first equality, and the second condition, the third condition gives us the second equality. So this tells us how to give a presentation for the frame of lower reals. And similarly, you can do something for the frame of upper reals. And actually, you might have noticed these frames are actually the same. They're isomorphic. So the lower reals and the upper reals are already the same thing. They're just like order reversed versions of each other. But we kind of talk about them separately because they do have this different order, and it would be confusing to use the same thing for both of them, because essentially the order reversing thing will change positives to negatives and things. We don't want to say that the infimum of something is some negative number if it's positive. So even though these end up being isomorphic, we'll talk about them as different things. Okay.
Did you want to join both?
Yeah. So I do want join in both because I guess we're using frames, so joins are the good things. But the difference is that if you look, the order's been reversed. So rather than the join of Q greater than P, it's a join of, I guess, so I say P less than Q. Oh, because we must have swapped Q and P. So maybe I didn't make this as close, as clear as possible. But essentially, because we've swapped P and Q and we've reversed, like, yeah, it turns out it's exactly the same. You've just reversed the order. So when in the one you had P greater than Q, you would actually have P less than Q. I kind of drew it in a confusing way because I also swapped P and Q in the two things. So it looks like they're the same, but they're the same except they've reversed the order. Okay. Good. So it's exactly like we did for talking about the locale of Dedekind reals, right? We just kind of throwing out half the axioms. And you might think, what does this give in terms of topological spaces? Did I talk about it? No, I didn't. So in terms of topological spaces, sometimes in analysis, people consider, for example, lower semi-continuous functions or upper semi-continuous functions. A lower semi-continuous function is just a continuous function into the space of lower reals. And an upper semi-continuous one is just a continuous function into the space of upper reals. So this is like so in terms of spaces, these are like the usual spaces of reals, but the topology, rather than being given by intervals or by being given then less than something and greater than something, it's either only given by greater than something or only given by less than something. So you just get these kind of one-sided intervals. And then there's also this difference because you actually include either infinity or negative infinity as appropriate in each case. But yeah, so these topological spaces do actually come up even in classical analysis. But there they think of them as having the same points, but a different topology. But there's no such thing as same points in different topology in point-free topology, really, right? So we say they're just completely different locales. Okay, good. So now we can actually find suprema, but I'm going to do one better than saying we can take a supremum over a inhabited set. We can take a supremum over a positive overt sublocale of the reals. And so in order to define, so the supremum is going to be a lower real. So how do you define a lower real? You define a lower real by saying which rationals are smaller than it. So now which rational lie in the set of lower bounds. So once we say which rationals Q are smaller than the real we're trying to define, that will be a definition as long as it satisfies the axioms here. So I claim we're going to say that Q is less than the supremum if there exists an X in V such that Q is less than X. So let's think, what does this mean? So we're smaller than the least upper bound. If we're strictly smaller than the least upper bound, there must be something in the set that we're smaller than, right? Because if we were smaller than if we were like greater than or equal to everything in the set, we wouldn't be strictly smaller than the supremum. Does that make sense? Okay. So we're saying to be smaller than the supremum is exactly the same thing as saying that we're smaller than some element. And we're doing this existential quantification. But remember, existential quantification is something we can do over overt things. So this is something which should be able to make sense. We can existentially quantify over V because it's overt. And we can say that Q is less than X because, OK, X is a real number. So we can ask when Q is less than X. That's one of the open sets for the real numbers. So I think this is maybe intuitive that this should give a lower real. But let's go and prove the axioms to make sure that it actually does. So remember in this thing LQ, this is a basic open set. So this was the name of the basic open set. And it's the basic open set of all things which are greater than Q, right? So it's the basic open set of all things where Q is an element of big L. So we're saying when we say Q is less than lambda, what we're really saying is lambda is an element of this basic open set, the things greater than Q. And we're saying this is true if and only if, and now this is new notation, but I'm saying that V meets LQ. So you can think of there being something in the intersection of V and LQ. So this kind of makes sense, right? Because LQ, it's all the things greater than Q, and then we have V, and if there exists an X in V such that it's also in LQ, that's kind of what we're saying. We're saying that V meets LQ. So this is just notation that means what I said before. But you can actually express this completely in terms of things we've spoken about. So what you can take is you can say, so LQ is an open, and then V is a sublocal of R. So what you can do is you can restrict the open to the sublocal. And then you can ask, is this open positive? And that's what this means. So it's saying that the restriction of LQ to V is positive. But that's just a rephrasing of what we had before. Okay. Now, one of the axioms of the reals is that we have this join. If you take the join of these LQs for all Q greater than P, that gives you LP. And this map, V meets with whatever. As I say, it's given by the composite of first this frame quotient, that's the restriction to V. And then this left adjoint, remember the left adjoints are what measure in an overt locale. This left adjoint to the street map is the map which measures whether something's positive. And that was a left adjoint, so that preserves joins. So it's the composite of a frame map and a left adjoint, so it preserves joins. So we can apply this map, V meets with something, to both sides of this equation. And this tells us that V meets with LP if and only if there exists a Q greater than P such that V meets with LQ. Are there any questions about that? Is that clear? Should I go through that again? Don't all shout out at once. So I have this equation for R. We're taking this map which says meets with V. This preserves joins. So if we meet with LP on the left-hand side, that's the same as taking the join of meeting with V on the other side. And joins in omega are just existential quantification. So that's just saying that if we meet with LP, it's saying that there exists a Q such that we meet with LQ. Okay. But so that's true now. And this is actually saying that we satisfy the first relation in this locale of lower real. So the first relation was this LP equals the join of LQ. But we've proved that if V meets with LP, then this thing holds involving LQ, V meets with LQ. That's if we rewrite that in terms of our definition of lambda being an element of LQ, that literally tells us that this condition holds. So this first condition holds. The second condition says that the join of all the LQs must be 1. And for that says that we want to prove that the join of all the LQs are 1 for, in this particular example, so we want to prove that lambda is a point. So in other words, there is some LQ that lambda lies in. But this is true because we know V is positive by assumption. So we know V meets with 1. So if you take, again, the meet with V on both sides, the thing on the right-hand side is true, so the thing on the left-hand side must also be true. So there must be some LQ that V meets with LQ. But V meeting with LQ is the same as Q being less than our lower real, right? So it also satisfies that condition. So it satisfies both the axioms needed to be a lower real. Is everyone happy with that? Okay. So I'm really just using this definition in terms of V and proving the properties, the two axioms that we need. Okay, we can do a similar thing with compact sublocales. So I told you before that the upper reals, you should think of them as being when we're taking infima. But that's when we're taking infima of sets. So it turns out actually if you take a supremum of a compact set, you get an upper real, not a lower real. And the way you can define this upper real given by a supremum of a compact set is, well, what we need to do is we need to say when is it less than a rational number. So the supremum will be less than Q if and only if everything in the compact set is less than Q. Again, hopefully this is intuitive from the definition of a supremum. The supremum should be a least upper bound, right? So if Q is an upper bound, if Q is larger than the least upper bound, it must be larger than everything in the set. And also, if it's larger than everything in the set, it should be larger than the least upper bound. Okay. So this is a way to talk about the supremum, but we're doing universal quantification. So this is now using the case compact. So I'm not going to go into the details of this one. It's kind of a similar story, but now we're using this compactness. So rather than restricting to V and checking whether it's positive, we're restricting to K and we're checking whether it is the top element. And the top, that's given by this right adjoint of this map streak. And we use it preserves directed joins, all these things about preserving directed joins that we spoke about for compactness. So that ends up being used to show this actually is an upper real, but it's pretty much the same story. Okay. So now the idea is, suppose we have a sublocal and it's positive and overt and compact. So because it's positive and overt, we have that it's we get a supremum as a lower real, and because it is compact, we get a supremum as an upper real. And so we claim that these are kind of the two pieces, like the one gives us our set of lower bounds, the other one gives us our set of upper bounds. But we technically need to show that they're compatible, right, to give us a single real number. So there are two things we need to check for checking it's a real number. And again, they correspond to interesting properties about when you have certain covers of something which is compact and overt. Essentially, the main lemma that comes down to is if you have a cover like U join V of something compact and overt, then either it's like either U is already a cover by itself, U is the top element, like U already covers it, or you have that V is positive, so V is not trivial. So that's kind of the thing you need to prove. But that gives us that this will actually be a Dedekind real. So again, I'm omitting the details. You can look at the lecture notes for all the details. But the idea is because it is overt and positive, you get a lower real. Because it's compact, you get an upper real. And then they actually end up being the same thing. They encode a single real number. So we can take the supremum of such a thing. Okay. So we know the supremum exists. So I guess classically, we didn't have to worry so much about proving the supremum exists. But we did need to show that it was a maximum classically, but this now showing this as a maximum is actually very easy, because remember, so the supremum, which we're calling rho, because it's a point of the reals, it's given by a frame map from the reals into omega, and we've kind of defined how it works, right? We need to say where all the basic opens go, and if this is something about being like greater than Q, then we use whether it meets K. And if there's something about being less than Q, it's about whether K is completely contained in the thing. So what we want to show is that this real actually lies in the sublocal K, which means the frame map factors through this quotient. So the fact it factors through the quotient means that it should only depend on the meets of every set with K, every open with K. But notice that K meets this open is precisely saying that the intersection of K with this open is positive. And K being contained in this open, it says that the restriction to K of this open is the whole thing. So already it's just determined by its intersection with K. So we already know that it lies in the sublocal K. So it is actually a maximum, not just a supreme. Okay, so since the image of a compact overt positive sublocal is compact overt and positive, we can actually, from this, get the extreme value theorem. Because if we have k being any compact overt sublocal, and you have a function from k into R, you can take its image. And its image will still be compact overt or positive. You can take its maximum value. This will be a Dedekind real number, and this will be the maximum. And then you need to show that the pre-image of this real number is still positive. And there's actually a number, like I'm omitting a little bit here. It's not very difficult, but there is a little bit of an argument to show that the pre-image is still positive. But it can be done. It's not nearly as hard as the things we've been doing so far. And that gives you the extreme value theorem. So the extreme value theorem, well, firstly, all the supremum exists. But secondly, if you take the pre-image of the maximum value, that's positive. Now, notice it doesn't necessarily contain a point. So containing a point would be the kind of non-point-free way of phrasing this. And this isn't necessarily true always constructively. But it is always positive. And so that's the thing that ends up being true constructively. Okay. Good. So that's the theorem. So now we can try and interpret it in any topos that we want. So we proved it constructively, and now we can say interpret it in a sheaf topos. So I'm not going to go into all the details of exactly what a sheaf topos is. But the idea is that for any locale B, there's a topos of sheaves lying over B. And what I will tell you is what all of these concepts, a locale, a compact locale, an overt locale, what all of these correspond to when you interpret them in this topos. So if you just living in the topos and you say this is a locale, and then you look outside the topos and you see what does this give? A locale inside the topos gives you a locale map into B. So it's a locale outside, but it's equipped with a morphism into B. And if you have a point of a locale inside the topos, outside the topos, this corresponds to a section of this canonical map into B. If you know that your locale is compact inside the topos, it means outside the topos, this map into B is proper. And if your locale is overt, it means this map is open. And the positivity of the locale inside the topos corresponds to these things being surjective. And the real numbers in the topos is just the projection of the real number of B cross R down into B. So again, so I'm not going through, because this isn't a course on topos theory, I'm not saying necessarily how you get this map of correspondences, but you can do this once and for all, right? And now that we know what all of these things are, we can use it to interpret what our result gives us. So our result, remember, okay, so it says that if we have something that's compact, overt, and positive, and we have this map F, then it attains this maximum value. So what do we have here? Well, our thing that is compact, overt, and positive, it ends up being a map from X to B, which is open, proper, and a surjection. So an open, proper surjection into B. Then we have a map F from X into R, okay? And the result says that we get this, this point, this maximum value, which is a point. So that gives us a section of this map from B cross R down into B. So this gives us a map row from B into R. And I haven't exactly written out the details of what this means localically, but okay, it makes sense what it is. And in fact, we can immediately translate this into spaces. So if you have a topological space, you can take the frames of open sets. And it turns out it's not very difficult to show that if you have a topological space and you have a map between the topological spaces, which are say open and proper, then the corresponding map between the frames of opens is also open and proper. So whenever you have a topological space and a proper open surjection, and you have a continuous function, then you can take the frames of opens and apply this result we had above. And what it gives is it says that this function, which you can define by taking the maximum of every fiber, you get a continuous function. So it tells you that this map, taking fiber-wise maximum, is continuous. So that's a result now just about topological spaces. No point-free topology, no constructive mathematics. It says if you have topological spaces, if you have a map from X into R, that's continuous. If you have another map, which is an open proper surjection, then you get this map by taking fiber-wise maximum of F, and that's a continuous map. So this is a result of classical topology, and a result that I didn't know before trying to see what this theorem gave. So maybe you haven't seen it either, but that would be something you'd have to prove kind of from scratch if you were doing kind of classical topology. But here we get it immediately as a corollary of the constructive result. So the constructive result, I mean, I'm not going to pretend the constructive result wasn't harder than the classical result for proving the extreme value theorem. It was harder, but now for free, we got this result in fiber-wise topology. And of course, I didn't need to interpret it in the topos of sheaves. I could have interpreted in a different topos, and then we get another result for free. So that's really the power of this approach. It's that you can take this extreme value theorem that we proved constructively now, and now you can interpret in different toposes, and you can actually recover a number of results just immediately as corollaries.
Do you know what it would be in the effective topos?
So it's a little difficult to formalize exactly what it gives in the effective topos in like an easy way, and because the effective topos is so difficult, it's hard for me to say precisely. But I mean, it'll say what you expect it to say. So it'll say that if you have a kind of real valued function, at least if you do it in the locale way, but that's a reasonable way to represent a real number. So you need to say what's computably overt, computably compact, all of these things, right? But essentially, it'll say that not only does this have a maximum value, but there's a program that tells you what the maximum value is. And then secondly, the positivity will correspond to not necessarily being able to find something that attains that maximum, but it will tell you that it'll tell you a way that you can notice when a certain open set contains all the things that attain that maximum, which allows you to like maybe approximate the points that attain the maximum. So yeah, so I don't know exactly what it's going to be, but yeah, it would be again something that says certainly what it does tell you is that you can compute precisely what the maximum value is of such a thing. But again, you need to check exactly what these notions of compact and overt are. Okay, good. Any other questions about this? Okay, good. So I just want to kind of give a summary of what we've done here. So we've seen that topology, it studies verifiable properties. We see that point-free topology, as opposed to kind of classical point set topology, it studies it kind of algebraically or logically using this lattice of open sets. We've seen that these frames, they can be presented by generators and relations, which is something nice that isn't true for topological spaces. We can see that these presentations of frames, they correspond to axiommatizations of these geometric theories, which describe these verifiable properties. For example, the theory of Dedekind cuts gives a locale of reals. We see that Hausdorff locales are those for which equality is refutable. In a discrete locale, equality is verifiable. See that you can universally quantify over compact locales and existentially quantify over overt locales. And then we've seen that if you have a constructive proof, you can interpret it in kind of a different topos, and you get a number of different results for free. But also that kind of, if you think topologically, some of these surprising things about constructive mathematics say that the subset of a finite set isn't necessarily finite, it becomes more intuitive, because who said that a subspace of a compact space has to be compact? And actually, using locales, many kind of classical results still end up being true with locales, even though they wouldn't be true for topological spaces. And this even includes kind of non-topological things like excluded middle or the axiom of choice. Okay, so if you want to see kind of more details about all the things in this course, you can see my notes that are on the archive at this address, and it'll give you both many more details of the things I covered here, but also a list of additional resources that you can look at it.